Thank you, Professor Yu. I'm now opening the first scientific session of this meeting. The first speaker is Joseph Avron. We call him Yossi, and the title is An Introduction to Zak Phase. Yossi?
So I think every talk should start with a joke. So there is a story about a scientist who, for the first time, came to give a talk in a scientific seminar in Israel. And after the first minute of his talk, a guy in the first row pulls out the gun and puts on the table. And after 3 more minutes, another guy puts a gun. By the time the third guy pulls out the gun and puts on the table in front of him, the speaker is so shattered and uncertain and shivering that one of the chairman of the meeting says, "Don't worry, it's not for you, it's for the one who invited you." So given this, I want to thank Moti and Amnon for inviting me. Okay. This year, Joshua Zak, a professor at the Technion, and actually my PhD advisor, was awarded the Israel Prize in Physics. And I thought that it would be nice to tell you about one of his works. And I'll start by telling you about the person. So Joshua Zak is now 93 years old. He was born in 29 in Vilna, Lithuania, and his childhood was hectic as the childhood of many Jews living in Europe. So from the age of 10 to the age of 18 or 17, he did not attend school. Instead, he was in a ghetto. After that, in a labor camp, and later in a death camp. He was liberated by the Russian army after making a death, how do you call it, Sadat Mavet? How would you call it, a death march? A death march from Stutthof. So he was then freed by the Russian army and immediately enlisted to the Russian army, where he spent another 2 years. When he was released from the army in 1949, a guy who had really very little education completed a secondary education with a silver medal after 2 years. At the same time, he did not neglect being the kayaking champion of Vilna. After graduating from the university, he went on to Leningrad, and in 1957, he chose to move to Israel, and he has been at the Technion since then. I think he has his most famous works are the Zak transform, magnetic translation, and the Zak phase, and I'll tell you about the Zak phase. Okay. You hear me without this mic, right?
No, we need it.
Oh, you need the mic. Can I turn this around? I don't. Okay. So I want to start by telling you a preliminary stuff, a very classical work that goes back to Michael Berry. And this deals with the geometry of 2x2 matrices. I think many of us are students of Joe Imrie, right? Who said that he can diagonalize 1x1 matrix. So the young generation can diagonalize 2x2 matrices. So I will not talk about anything more complicated than 2x2 matrices. Now, the nice thing about Hermitian traceless 2x2 matrices is that they can be represented geometrically as a point in free space. So if I denote, I prefer to use my pen, if I denote by X and Z the Pauli matrix, the Pauli matrices, and Y is the product of the two, up to a factor I, and little x, little y, and little z are real numbers, then every matrix can be represented in this form, is written up there, in this form. And therefore, every matrix can be associated with a point in 3 dimensions. Now, it is interesting. Now, usually, a 2 by 2 matrix has 2 distinct eigenvalues. But sometimes it has only 1 eigenvalue. In the case of 1 eigenvalue, where the 2 eigenvalues become degenerate, is a singular point. And the way to explain why it is singular point, it's the origin of the space, right? The case where the matrix is degenerate is the case where x, y, and z are all equal 0. And then this matrix H trivializes. So you can see this if you look at the spectral projection associated with the Hamiltonian H. Probably this is the point when I start losing some people, definitely the biologists, no? Anyway, so the spectral projection is made of hat H, which is H divided by this denominator, which is singular at the origin. And therefore, it is, if we are interested in spectral projections, in the eigenvalues of these matrices, we want to remove the origin from the space. Now, 3-dimensional space has no interesting topology. It's a boring space. It's contractible. You can contract it to a point. But if you remove the origin, it gains an interesting topology. And because it has interesting topology, this is going to play a role in what follows. So as I mentioned, the origin, the point where eigenvalues cross is a singular point. I remove it from the space, and this endows the space with an interesting topology. Now I want to talk about the geometric notion of parallel transport. I'm going to stick with 2 by 2 matrices, and then every eigenvalue of a 2 by 2 matrix can be described by a point on the Bloch sphere. Again, just a 2-dimensional sphere. Every point every eigenvalue of a matrix can be associated with a point on this sphere. And now I want to ask the following question. What does it mean to take a point on the Bloch sphere and move it, a vector in the Bloch sphere, and move it parallel to itself along the Bloch sphere? And Levi-Civita, a great Italian geometer, told us what is the definition of parallel transport. So parallel transport is expressed by this equation, where the equation says that the variation in the vector, you don't see variation in the vector in the direction of the vector. So if I project the variation of the vector in the direction of the vector, I get 0. Now, in general, psi d psi is a complex quantity. Its real part guarantees that parallel transport preserves the normalization of the vector, and the vanishing of the imaginary part says that it keeps its phase. So, since some of you don't normally think about parallel transport, let me consider an example. So rigid rotation of the Bloch sphere is expressed by e to the I z phi over 2. Phi is the angle of rotation. Z is this Pauli matrix that we know about. Now I consider a rigid rotation of the Bloch sphere. And I ask, if I take a rigid rotation of the Bloch sphere and I pick a point, say, on this latitude, is it being parallel transported or not? It turns out it's very easy to compute that psi d psi is the expectation value of z. This means that only the equator is being parallel transported. Okay? Now, in fact, some of you may know this when you visit museums and you the first thing you usually see in the Science Museum is a Foucault pendulum. Well, there is a point, there is one latitude where science museums don't have a Foucault pendulum. Do you know which one? Which latitude no museum would put a Foucault pendulum? That's right, on the equator. It doesn't do anything, right? Because it is being parallel transported. So it doesn't change the direction. Therefore, this is similar here for states on the Bloch sphere. So parallel transport occurs along the equator. Okay, but at all other latitudes, we get interesting parallel transport are not being parallel transport, or rigid rotation is not a parallel transport. Now, there is an interesting thing about parallel transport, that if you complete a cycle, it may be inconsistent with itself. There is a conflict with parallel transport. So if I parallel transport, for example, if you think about, let's take the example that I did before with this motion on the equator. You remember that rigid rotation was given by e to the I z, the angle divided by 2. So a 2 pi rotation is e to the I z pi, but e to the I z pi is -1. This means that after a full rotation, a parallel transport, the vector doesn't come back to itself, it flips its sign. This flipping sign is called holonomy, and it's a special case of a more general formula shown by Berry, which is like this. Take any family of Hamiltonians. We said that any Hamiltonian can be described by a point in 3 dimensions. So a one-dimensional family is described by a closed loop. So a closed loop is associated with the vectors, which are the projection of this loop on the unit circle. And Michael Berry, and in fact, they are the top picture is associated with the top eigenvalue and the bottom circle with the lowest eigenvalue. Now, look at the spherical angle of this orbit. It was shown by Michael Berry that half the spherical angle is the holonomy. So this will be the mismatch of parallel transport along such a thing. Now, this is defined as Berry's phase. It is geometric. In what sense is this geometric? It is geometric in the sense that the rate at which you do things doesn't matter. You can do it fast, you can do it slow, you always get the same phase. But it is not quantized. In general, the spherical angle depends on, it can be big, it can be small, it can be anything. Very good. So far, so good. I lost the interest of those who couldn't follow, and I lost the interest of those who know these things anyway. Right? Okay, now I want to describe the relation between 2x2 families of 2x2 matrices and one-dimensional Bloch Hamiltonians. So I want to focus on one-dimensional chains where the unit cell has 2 atoms. So this is shown on the top line. Now, it turns out for me to be convenient to redraw this picture so that I draw the unit cell vertically, like so. And then, because there are 2 atoms per unit cell, if you write the Bloch decomposition associated with a single fermion moving in 1 dimension is described. Of course, if you don't know about this Bloch nonsense, then this doesn't mean anything to you. But I'll assume that some of you know more than I do. And because of the periodicity of the problem, there is a conservation law, and the conservation law is known as the Bloch momentum. And if you study the problem for a fixed value of Bloch momentum, you get a 2 by 2 matrix. Why 2 by 2 matrix? Because you have 2 atoms per unit cell. Now, the matrix depends on this Bloch momentum, and the Bloch momentum, it depends continuously on the Bloch momentum. In fact, it depends smoothly on the Bloch momentum, and it depends on the Bloch momentum periodically. Why does it depend on the Bloch momentum periodically? Because this is basically a Fourier decomposition of a discrete series, and a Fourier transform of a discrete series, a periodic function. So h of k is a periodic 2 by 2 Hermitian matrix, and therefore we can think of such h of k, if we think in terms of the x, y, z, which appear here, then this is just a closed loop in 3 space. There is no clock in here, and I have no idea how am I doing with time. Someone will tell me? Amnon, who is the chairman? What?
11.
And how much time do I have? What?
15.
15 minutes. Okay. So now after wasting half of my time, I can tell you what is the definition of the Zak phase. So Zak phase is Berry phase for one-dimensional Bloch band. Now, since we are considered 2 by 2 matrices, we have 2 bands. And in general, the phase, as I said, Berry's phase is a geometric notion, but has no topological content in it. And this is shown here. You see, you can move this loop, and the spherical angle will shrink or increase. However, there is a special case where this phase is quantized, and this is the special case where the loop lies on the equator. If the loop lies on the equator, then there are only 2 possibilities. Either you make a full circle surrounding the origin, or you don't surround the origin. So the phase is characterized, it gains a topological significance, and this topological significance arises because of symmetry, because in this case, because it lies in the equator. So in this sense, the Zak phase is the mother of symmetry-protected topological phases. It's the simplest example of a symmetry-protected topological phase. Good. Now there is a comic relief, right? So I wanted to tell you about a topological invariant from the 16th century. And I think this is appropriate for our friends who came all the way from Korea. And it was discovered actually by Mr. Magellan. Actually, not by Mr. Magellan himself. By the time it was discovered, he was dead, but by members of his crew, especially the geographer or the chronicler he had on the ship. And Magellan was the first person to circumnavigate the Earth. And he decided to circumnavigate the Earth going west. By the time they crossed the Pacific Ocean and arrived at islands, of course, they kept a very careful log on the ships. And by the time they arrived in, I don't know, in the Philippines, Manila, they discovered that they missed a day. That they thought it was Wednesday, but in fact it was Tuesday. So this is what happens when you travel west, when you circumnavigate the Earth. Once, you lose a day. If you circumnavigate it in the opposite position, you gain a day. Do you know who made money out of the fact that you should move west rather than east? East rather than west? Anybody knows about children literature? That's right, Joon. Right, they gained the day because they moved in the opposite direction. So here's a picture of Magellan. I don't know if it's true or not. Good, so now I want to talk a little bit about when the Zak phase is topological. So I mentioned that topology has a lot to do with the fact that we removed the origin from the space, from our three-dimensional space, and it also has a lot to do with the fact that we are going to impose a condition of symmetry. So one example of a symmetry is chiral symmetry. I define, this is the definition. I say that HK is chiral symmetric if HK, if I multiply by Z, conjugate by Z, flips the sign, where Z is this Pauli matrix. Now, if you check which kind of matrices satisfy this condition, you see that H of K must have no elements on the diagonal. This means that the Z coordinate is set to 0, and only the XY coordinates are allowed to be different from 0. Now, you see, is it okay if I say pi 1 of S2 is 0, but pi 1 of S1 is Z? Is this okay? Some of you like it, okay? So if you are in the plane, and you take a plane, and you take a circle in the plane, which is punctured, a punctured plane, then not all circles are topologically homotopic. And in fact, curves are then classified by the winding. You can think of the plane as a complex plane, XY is a complex plane, and the topological invariant is associated with the winding of the curve around the origin. And so this is a situation where Zak phase is topological. Now remember, you remember that the relation between Berry's phase and the spherical angle was with the factor 2. If I have an orbit on the equator, the spherical angle is 2 pi. But to get Berry's phase, I have to divide by 2. So the Berry's phase is pi, and therefore, in the case of chiral symmetry, Berry's phase is quantized to be either 0 or pi. That's all that it can be. So that's a case of a topological thing. Now let me, אני רוצה להכניס איז. How am I with time? I'm not. 12 minutes, okay. So I can bring in a goat and then take it out. So there is something weird about this Zak phase that I want to talk about. And the fact is that it appears to be a gauge-dependent quantity. And let me explain in what sense. So you remember I told you that I wanted to draw my crystal with 2 atoms per unit cell like that. And I previously choose the unit cell like this. But there is no reason why I couldn't choose the unit cell like this, or any other pair, right? I could pair any point from the bottom row to any other point on the top row. Now, you can ask the question, if I change my notion of unit cell, how does this affect the Bloch, the 2x2 matrix, the periodic 2x2 matrix that I have? And it turns out, you have to believe me, that the 2x2 matrix changes by a diagonal unitary. And physicists like to call diagonal unitaries gauge transformations. So it changes by a gauge transformation as shown here. Now, a gauge transformation, a diagonal unitary, doesn't change the spectrum. So the band spectrum is the same no matter how you choose your unit cell. But it does affect the eigenvectors, and it affects the Zak phase. So the Zak phase depends on the choice of unit cell. In particular, in the cases that the Zak phase is quantized, by changing what you call the unit cell, you can flip the pi to 0 and the 0 to pi. And this makes one worry, is this a measurable quantity? Okay, so let's in case, let me be concrete and let's consider a famous model which is called the SSH model after Sue Schrieffer-Heger. And this is the model. It's described by this Hamiltonian. It describes a one-dimensional lattice where there is no, all atoms see the same local potential, but the hopping from this pair and the hopping of this pair has different amplitudes. So one of them I call S, and one of them I call T, and they have this staggered amplitude. If I pick my unit cell to be this pair S, and I pair my Hamiltonian like this, the Bloch Hamiltonian looks like this, where S comes without the K and T comes with e to the ik. But if I choose this type of unit cell, then the role of S and T is flipped, and it is S that comes with ik, and T doesn't come with a K. And this has the unpleasant consequence that the Zak phase can take any values, right? It can be pi or 0, depending on the choice of S or T, and depending on whether T is bigger than S or T is less than S. You can actually see that it's 0 and pi. Do you want me to go over it, or you see? You see, for example, take like this. Consider this term. Put S equals 0. Then you see that this term, T e to the ik, makes a one rotation. So if T is the dominant object, you should get a pi. But if you put S large and put T equals 0, then it just sits there. It doesn't wind. So this is why you get this nice table. So one may worry that this Zak phase has these unpleasant features that depend on the unit cell. And I want to show to you that actually this is not something you don't encounter in physical phenomena. And an example is polarization. So suppose I have this one-dimensional lattice where the gray atoms, say, are negatively charged, slightly negative charged, and the red atoms are slightly positive charged. And I would ask you, what's the polarization of such a crystal? Then you would say the polarization should be determined by the polarization of this atom or molecule, right? But this depends on my choice of a unit cell. If I choose this as my unit cell, then the polarization is different. And this is the same ambiguity as the ambiguity of the Zak phase. Now, there is a deep connection between Zak phase and the modern theory of polarization as developed by people like Resta and Vanderbilt, but I won't talk about this much more. Let me conclude. How much time do I have?
5 minutes and then 5 minutes discussion.
Okay. So let me conclude with an experiment that measured the Zak phase in spite of this ambiguity. And the experiment was done on cold atoms. It was not done on one-dimensional. It's not one-dimensional conductance problem of electrons, but it was done on atoms cold atoms in a periodic lattice. And it was made by, it's an experiment of interference. And I like to call this interferometer the Bloch square interferometer. Why Bloch square? Because the man who built the interferometer is Emanuel Bloch at München. And what it measures is the Zak phase of a Felix Bloch band. So there are two Blochs in the story, one alive, one dead. And the beautiful arrangement that Mr. Bloch succeeded in doing is shown in the picture here. In order to make an interference experiment, you want to interfere something. Now, usually, when we look at the interferometer, we take a particle and we split the path in ordinary space, and we recombine the path, and then we watch interference. Now, Bloch did something different, and it's beautiful because it's different. He split the path in k-space, in momentum space, not in real space, in momentum space. So this is what is shown here. He took, in momentum space, he took an atom, forced an atom to go one way and to go the other way in momentum space and then interfere. And the beauty of his interferometer is the following thing. It was arranged so that the Zak phase interferes constructively, and all other phases, like the dynamical phase, phases due to noise, interfere destructively. So I'll give a sketch of his idea, but first I want to explain how did Immanuel Bloch got around the problem of ambiguity of Zak phase and its dependence on the choice of a unit cell. So he decided to make an experiment where the change was gauge invariant. You could not argue about the change. And this is how he did it. So his lattice was an optical lattice, which is shown here. And the lattice was so that, atoms could hop for had the small barrier here and a large barrier here. This is correspond to the S and T that I showed you before. And he could more or less instantaneously flip from this crystal to this crystal. So he could replace S and T to T by S. This is an objective replacement. He does not care about how you choose the unit cell. Pick a unit cell, but no matter which unit cell you pick, I'll flip on you the S and T. And then what he measured was not the Zak phase in one configuration, but he compared the Zak phases in the two configurations, ST minus TS. And he showed that it's always pi, which is what you expect, because I told you that by, I told you this when I showed you this model. So this is a schematic of now the other thing which he did, I like this a lot, he made a spin-induced schizophrenia. And let me explain how he did this. So he took atoms that also had spin. And one thing you can do with spin is described by this Bloch sphere. The spin can point up, can point down, but you can put the spin in a superposition. So now he had these atoms which you could put in a superposition, and he made an arrangement where spin up would go to the right and spin would accelerate in one direction, and spin down would accelerate in the opposite direction. So by making a superposition in spin, he forced the poor atom to have to be schizophrenic, so that part of it went accelerated to the right, and part of it accelerated to the left. So, and the acceleration caused by the spin was done by making a magnetic field with a gradient, and this is the Hamiltonian corresponding to this. And as a consequence, he could make the following interferometer. Right? The spin up would take this route, spin down would move in k space in opposite directions. And then after they reached the edge of the Brillouin zone, the spin up continued on this path, the spin down continued on this path, and they interfered at the top. I'm not doing justice to all the details of this experiment. Now, in the interest of not overburdening you with stuff, this interferometer also gets rid of the dynamical phase, but I won't explain this. And now let me conclude with a short history of all these phases. So there is a nice statement, I think, due to Arnold, which you can find in Michael Berry's homepage, which says that nothing is ever discovered for the first time. And in fact, so Berry's phase had a precursor many years before by Pancharatnam in 1956, where he studied polarization. The Zak phase had a precursor in 1979, where Mead and Truhlhar, who studied Jahn-Teller effect, realized that they could determine whether or not two eigenvalues cross by measuring this phase. And I'll just go through the list and finish. And now there is a backward arrow in time. In 1983, Barry Simon published a paper which coined the term Michael Barry's phase, and he also introduced the notion of a Chern bundle. And this paper appeared before Michael Barry's paper. This can happen, you know. The two, in fact, Barry Simon and Michael Barry met in Australia. Michael Barry told about his phase to Barry Simon. Barry Simon wrote a short note, sent it to PRL, and it appeared immediately. Whereas Michael Barry's paper, which was sent to the Royal Society, you know, a referee sat on it for 7 months. That's okay. Anyway, I think history, this didn't hurt either of them. Yoshua Zak came with his phase in 1989. Resta and Vanderbilt in 93 made this new theory of, modern theory of polarization. And in 2013, Bloch measured the Zak phase. Thank you.
Thank you, Yossi. The lecture is now open for discussion. If you want to speak, please push the button on your microphone. Yes, please.
Thank you for your nice talk. I have a short question. By the way, I'm Gil-Young Cho from South Korea. And I have a question on your core atom experiment. And can you generalize your, I know it's not your work, but is it your work, sorry. Can you generalize that to the other topological phases? You know, there are many different topological phases, like Chern insulators and higher order topologies. Can you generalize them to detect the topological invariance of more general topological insulators?
I think it's a great question, and I don't know the answer. I've not thought about it, so I would not like to just do it. Yes?
Please.
Oh. Thank you. Well, thank you for a very nice talk. You mentioned about the ambiguity of this Zak phase, which comes from the choice of unit cell, and you mentioned it's on gauge symmetry. And I'm slightly confused. It seems to me like degeneracy. If you think about some kink configuration, you mentioned about measuring this Zak phase, and if it depends on the choice of unit cell, and if it changes from 0 to pi, what about if your half of that has 0 configuration and the other half has pi configuration? Then you can really distinguish that, isn't it?
Yes, you're absolutely right. In fact, if you take, this is one very natural way of comparing Zak phase is to take one material which has Zak phase, say unit cell, to take, for example, the SSH model, but make a mistake, take one link out and then connect them, and then you compare a system with S larger than T with a system S less than T, and then the Zak phase manifests itself by 0 mode, by a solid time. So this is also a comparison. So the point I was trying to make, that the right notion of measuring the Zak phase is always to compare two things. So Bloch did the comparison by flipping the crystal, but a simpler method is, as you suggested, is just to take two two crystals that don't want to live in peace, and this is something we have here all the time. Yes.
Yeah, maybe just to add to that, so usually a natural way is to compare to the vacuum, where the Zak phase is trivial. So this is why you have edge modes, if the Zak phase in the material will be pi.
Right.
Thank you.
Yes, Hadar.
Yes, so with respect to
Push the button.
No,
okay. So with respect to the previous question and Yuval's comment, there's recently some work on measuring SSH systems using microwave waveguides, and I wonder if there's any, if you're aware of any method to see the Zak phase in this kind of system. For example, people claim to actually see the zero mode in the spectrum. So would that constitute a proof that there's a well-defined Zak phase in such a system?
So I don't know about this experiment. Tell me more about it.